Up on the screen, I have a picture of a cell phone, and I want you to think just a bit about what cell phones do for us. They do amazing things. I mean, they aren't just telephones. They allow us to do text. They allow us to run all sorts of applications. I particularly like navigation. And not only that, but we get to talk to them, so they do speech understanding. In order to do all this stuff, they run a huge amount of software, millions of lines of code. And this code works, and we expect it to work. But you know, it wasn't always that way. And data abstraction is a big part of why that code works. And I'm going to tell you today about what data abstraction is and sort of how this came about. I grew up in San Francisco. This is the Golden Gate Bridge about that time. And when I graduated from high school, I went on to Berkeley. This is the Campanile. We called it Cal. And I was always interested in science and technology, engineering, not engineering, science. I came from a family where my father was a lawyer. I didn't know much about technology. I majored in math. And when I finished my math degree, I decided I wasn't ready to go on in graduate school in math, and so I decided to get a job. And I looked for a job, and I couldn't find anything interesting in math, but I was offered a job as a computer programmer. I didn't even know there were computers. And of course, I had no training. But the truth was, nobody coming out of college in those days had any training because there was no computer science program for us to have studied. So they were hiring anybody who walked in the door that they thought might be able to do the job. So my first day on the job, I was handed a Fortran manual and asked to write a little program to do something. And there's a picture of the Fortran manual, and that's a picture of John Bacchus, who was one of the people who developed Fortran. And I learned how to write in program. I wrote this program to do whatever it was they asked me to do, and I found that I had discovered a field that I really liked and that I was really good at. I worked for a year in this job doing programming in Fortran. Then I moved and took a different job where I was doing programming in machine language, in other words, directly in the language the machine supported. And partway through that second job, I decided that it was time to go to graduate school because I was entirely self-taught. And although I was learning a lot very fast, I thought I could learn a lot faster. So I went to Stanford. This is the quad at Stanford. There actually were very few places to choose between in those days. MIT was one of them, but MIT didn't seem like the right choice for me. And I wanted to get back to California anyway. So I went to Stanford. They didn't have a computer science department yet. They just had a program. And I think there were only 5 or 6 people that were admitted in the year that I went there. I ended up working with John McCarthy. I'm sure John's picture was up there on that slide that was shown to you earlier. He was one of the pioneers of artificial intelligence. And my thesis was in chess. Chess was a hard problem then. Computers were not very powerful. They were not capable of doing the kind of deep search that is required to play chess. And so we had to invent heuristics to try and make them work. And I specifically was working on chess in-games, and that's a picture of me at about that time. And notice up on the title page there, my name is Huberman. That was my maiden name. Okay, so what happened when I finished graduate school, and this is about 1968, I had decided while I was a graduate student that I wanted to move out of AI and into computer software systems. I decided to finish my thesis in AI and make the switch after I graduated since I thought I would get finished with my PhD faster that way. At this point, I took a job with the same company that hired me fresh out of my undergraduate, only this time I was working as a researcher rather than a programmer. And my first project was to design and implement an operating system, a time-sharing system that allowed multiple people to use the same computer at the same time. Because as you heard earlier, computers were much too expensive in those days for anybody to have their own PC. But having a time-sharing system meant that you could be sharing a computer with somebody else and you got the same experience. You felt like it was your computer, you were online, even though you were sharing it with other people. Now, when I finished this Venus system, now it's about 1970, I was asked to look into the software crisis. So what is the software crisis? We don't have a software crisis today. I mean, there are problems with software, but nothing like what I'm talking about. The software crisis was people did not know how to build software systems. And it was not uncommon in those days, and this is through the 60s, the 70s, even into the 80s, to pick up a newspaper and there'd be an article there. It would say, Company X spent millions of dollars, hundreds of man-years, to build a program to do something or other. And in the end, they had to throw the whole thing out because it didn't work. So there was a serious problem here. The hardware was coming along nicely, but people did not know how to build the software. And of course, without the software, there was no way to get these computers to do anything interesting. So what to do about this? Clearly a really important problem. So of course, I did what any sensible person does when they're moving into a new field. I read the literature. And there was a programming methodology community out there working on this problem. And there were a lot of good papers and very good people writing these papers. And what I'm showing you here is some very distinguished people in computer science whose papers I read. There were other papers by very good people that I read also, so I'm not trying to limit the task here. I went back and read these papers, and they're very good. It's good to go back and look at them. So I read all these papers, and I discovered that they were talking about two different but closely related topics. One was the question of how do you design software. The other one was the question of how should the software be structured. And the two problems are closely interrelated. So I began to think about this, and in particular, I started to think about this question of how should software be organized. And what they were talking about was something they called a module. And they didn't know what a module was. And in fact, Dave Parnas, in one of his papers, said, I know we need modules, but I don't know what they are. And that was actually the state of the field at that time. What a module is, it's a black box. That's why I have a black box up here. And the idea is that it has an interface, and you can understand what this interface is. It gives you some sort of functionality. But you have no idea how it's implemented. You can't see inside. And here's a non-computer science analogy, a radio. Okay, a radio has a simple interface. It's got a few knobs. You can turn it on. You can turn to a different station. You can change the volume. Inside, lots of stuff is going on, but you don't have to think about this. This is clearly not a computer science thing, but it's the very same idea. So people wanted these modules that they didn't understand, and they had a dream that programs would end up just being a collection of modules. Every piece of code would be in one of these modules. What I'm showing you here is a system with 5 modules, and the arrows tell you that one module is implemented making use of the interface provided by another module. So think about each of these modules has an interface. This interface is described by what we call today a specification. And then inside there's an implementation that realizes the specification. And you can use a module without having to understand how it's implemented. You just have to understand its specification. The glory of this, if we could figure out how to do it, is locality. We can work on that system one module at a time, all separately. You can hand out these modules to different people to implement, and in the end, you'll be able to put them back together again, because if module B implements its specification, then module A, which is depending on that specification, will be able to use it just fine. In order to make this work, you want those to really be black boxes, though. You don't want module A to be peeking into the inside of module B to see what's really going on, because then you'd be violating that abstraction barrier. So this was the dream. We need these modules, just we didn't know what they were. There was one modularity mechanism in existence at that point, and this was the procedure or subroutine. So people knew that you could implement something like a sort routine, and to the user what this meant was I can give you a list of strings, and that sort routine will return that same list to me, but now in sorted order. And I didn't have to worry about how it was implemented. I only had to worry about what its specification is, what it did. But sort routines were not going to do the job here, because we needed a lot more from our modules. They had to be able to do a whole bunch of things. And not only that, but they had to have memory. If you think about that radio remembered. When you turned it on, it was on, and after that, you could change the station. We needed something similar for the software. So I read these papers and others that I haven't mentioned, other authors that I haven't mentioned, and I realized that in the design of Venus, the system I first implemented at MITRE, I had invented a methodology. And I invented this methodology because I was concerned. I had a small team of programmers working with me, and I didn't know how we were going to be able to build what was really basically a very complicated system in a short period of time. And so I had invented a methodology. This is the paper where I described it after I realized what I had done. And the methodology was simply the following. I had a special kind of black box, which I called a partition. It's just a black box like what I showed you before, but it's got some more structure. Those lines are operations, and the rule that I invented for Venus was that each partition offers a set of operations. All the rest of the code in the system can interact with the partition, but only by calling those operations. And then inside was hidden stuff. The implementation was all inside, and that included state as well as a program. So if you think about this as a radio, you see there's a knob there to turn it on, a knob there to change the station, and so on. The same kind of idea. Of course, a radio is not software. So here's a little example that's closer to the software kind of stuff that Venus was doing. Remember, it was a time-sharing system, and so that meant the users had to share the peripherals. And by the way, in those days, mag tape was what we used to remember stuff. And this is a teletype. This is the kind of printer we used to use. So we have a bunch of users online in Venus, and they all want to use the printer simultaneously. Well, we got to sort that out. So the way we sort it out is we build a partition. It's the controller for the printer. Each user who wants to use the printer calls an operation saying, here's my job. Later on, they could call a different operation saying, is my job done yet? And then there was some code off on the side that was actually running the printer, and when it finished one job, it could notify this module and then get the next job. So that's the kind of stuff I was doing in Venus with this partition. Okay, so now it's 1972. And in 1972, I moved to MIT because they were actually looking for women then. Things had changed a bit. And you see me sitting here with Jack Dennis, who is a well-known professor in the computer science department, and he was one of the people that got me to come to MIT, and he was also very helpful to me when I first arrived. This is about the time I moved to MIT. And it was a great time for me to move to a university because when you're at a university, you have the freedom to decide what research you're going to work on. It's both a blessing and a curse, of course. You have to have the ideas that lead to those research projects. And I had a project that I was absolutely passionate about. I really wanted to understand what this modularity stuff was. And the thing I was really thinking about was, it seemed to me we had several papers that described systems broken up into modules, and they made a very good case for this being a good organization for the particular system they were using. And you would look at it and you say, yeah, that's a good way to organize it. Those are sensible modules, and that's what I'd like to do. But when you tried to take those ideas away and apply them to your own system, you couldn't do it. There was just some sort of disconnect between what was written in those papers and what you needed to be able to think about these ideas in the context of your own work. And so I was thinking about this. I was really obsessed with this, and I was thinking about it at night. I would think about it going into work. I was thinking about it all the time. And one day in the late part of 1972, the early part of 1973, I all of a sudden saw that I could relate a module to an abstract data type. So it was like I made this connection I just hadn't been able to make before. And I said, I'm thinking about a data type, and what it does is it defines a set of objects, but it also defines operations, and those operations are the only way that you can interact with an object. And if you think about this, it's just a partition. I mean, that partition is an object. And when I look back at the literature in this field, I saw ideas that were like abstract data types floating around. It's just that nobody quite made the step. And what's important about this step is that it relates a thing that was just a structural idea to an abstraction. And abstraction is the way that we design our program. So that was a very important intuition. Well, it was just an idea. So the next thing I did was to work with Steve Zillis. Steve Zillis was a graduate student at MIT, and he had a similar idea. So we started to work together, and we worked together for maybe 6 months, maybe 9 months, something like that, over the course of several months until about the end of the summer of 1973, and by then we had solidified our ideas and we wrote this paper, the first paper that describes the notion of abstract data types, and that was in the fall that we finished of '73. Okay, at that point, I decided to start working on a programming language. So that paper had sketched out the idea of abstract data types, and it had proposed a sketch of a programming language. But it was by no means a language that worked, it wasn't complete, and I decided it was important to finish up this work. I wanted to have a real language where programmers could write real programs, and we could see whether they found the use of data abstraction useful, and we could see whether they liked the constructs that we provided and whether the programs performed well enough and so on. So I decided to take on this job of working on this language that we called CLUE. It took about 5 years to design CLUE. First of all, so why did it take so long? First of all, programming language design is actually really hard. Anybody who has worked on a project like that will tell you that. But in addition, we had to actually set off in new directions in many different fronts because there was nothing like this already. It's a big step from having a few procedures that can do some abstract things and having all these new data types. Of course, we had to build some mechanism that allows you to define an abstract data type. That was the cluster, and the name CLUE comes from cluster. But we also had to innovate in many other directions. For example, in those days, exception handling was not built into most languages, and people didn't even know what form it should take, so we had to think throughout all of that. The iterators had to do with the fact that data types are often collections, and if you build a collection of something like a set, then you often want to iterate over it in a non-destructive way, doing something with all its elements, so we had to figure out how to do that. In some sense, polymorphism is the most interesting thing we had to do. Polymorphism means many types. And as soon as you have a language where programmers can develop their own data abstractions, so you're going to have many different data types, you can see that you're not going to be able to be happy with modules that are focused on a single data type. I mean, I wouldn't want to have to write a sort routine every time a new data type comes into existence. That would really be a pain in the neck. So we need to be able to write a sort routine that works over many types, and it took us a long time to figure out how to do that. I should say that we were looking for what's called strong typing, which meant that the compiler for the language was going to do all the type checking to enforce all the rules, and there was a lot of uncertainty about whether that was all going to work out. Okay, so now it's about 1978, and we have finished the design of CLUE. Here's the CLUE reference manual, and the main thing I want you to notice there is all the names that are on that paper, because these were all students. I designed CLUE with a bunch of graduate students. I think Elliot Moss was actually an undergraduate, and we all worked together, so it was a group project. And this has been my experience at MIT. It's been wonderful working with groups of students. Okay, so now it's 1978, and I'm looking around for what to do next. And I happened to read a paper by Bob Kahn about the ARPANET. So the ARPANET was the precursor of the internet. And up on the diagram, up on the screen, I have a little diagram of the ARPANET as it existed then. It's a network. It connected together a few universities and research institutions. And they are represented on the slide. You can see MIT there running a PDP-10, and UCLA running a something or other. So they're all running these old computers. And these computers are connected to the network by these things called IMPs, which then use the technology of the network to communicate with each other. And Bob wrote in this paper that he had a dream that people would write distributed programs. And what this meant was a program that would have components running on these different computers, doing parts of that program and communicating through the network. And nobody knew how to do that, so I thought, gee, here's a great opportunity. And so I jumped into distributed computing. And most of my research from then on was really focused on distributed computing, although I continued to work in program methodology at least throughout the 80s. So this is really the end of the technical part. I'm just going to tell you a couple things that happened after. The first one was around 1990, Java came along. So Java was the first mainstream language to support object-oriented programming. And object-oriented programming is actually a mixture of the data abstraction work I did in CLUE and the inheritance work that was coming out of Smalltalk. That was Alan Kay's group that developed Smalltalk. An East Coast team and a West Coast team. I always think of it that way. We're working on different stuff. And there was a gap here of 10 or 12 years before the technology moved from research into the mainstream. This is not an uncommon kind of gap to have in technology. Okay, the second thing is when I got the Turing Award. This is now 2009. That's when I got the Turing Award. And this caused me, when I got the Turing Award, to stop and think about what had been happening in my absence, in the sense I'd been focused on distributed computing. I wasn't paying much attention to program methodology. And what I discovered was a remarkable thing. Programming today, modularity based on abstraction is the way things are done. This had become so embedded in the programming culture that my own graduate students didn't realize there was a before. They just thought this was the way things were. And my husband was on the internet every day when I got the Turing Award, because there was lots and lots of stuff coming out. And one day he saw a quote by someone who said, "Why did she get the award? Everybody already knows this." So I think we can see this wasn't meant in a kindly way, which of course, but it was actually a real justification of what I just said. That was how it was. And that's the end. Thank you.